All right, how's everybody doing? Yep, couple of thumbs up. Remember, if you can turn your cameras on, please do so. Helps me see your faces, helps me know what's going on. Oh, and also you can't see my face. There we go. All right, we're starting to wrap things up. There's only 3 weeks of the semester left for coursework, and next week's gonna be an exam. So we don't have a lot of time left to cover all of the things that I said I was going to cover in the syllabus. So I'm trying to pick and choose what are the most important things. If you read ahead and you find a topic that you'd really like to know more about, let me know and I'll make sure I cover that. But yeah, right now I'm going to pick and choose some of the things that I think are important to know. I mean, it's all important to know, but also your textbook sometimes goes into too much detail into the unimportant things. So yeah, I'm gonna just choose some of the things to talk about and some of the things to ignore. All right, so just a little bit of a recap on what we did last time. So let's see here. We were talking about the hydrogen atom and the hydrogen atom wave function. And we said that the wave function depends on these 3 quantum numbers, n, l, and ml. And they can come from these various functions: the radial wave function, which depends on n and l, the theta function, associated Legendre polynomial that depends on l and ml, and then there's this phi part that depends on just on ml. So those are the 3 quantum numbers, and we said could be 1, 2, 3, any positive integers. L could be 0, 1, 2, or so on up to n minus 1. And ml could be 0 plus or minus 1 plus or minus 2 up to plus or minus l. So those are the wave functions that we came up with using various different models. The last time we left, we talked about probabilities. And let's say you have an atom, right? That's the nucleus, a hydrogen atom, and the electrons somewhere out here. I'm going to draw this as this. Let's say you drew a line from that atom out to infinity, right? That's the some line drawing the radius. And you wanted to find a probability between any 2 points along this radius, right? So it'll be the probability of finding the electron sort of in that little shell. And that probability would be equal to, let's say this point is A, that point is B, right? It'll be the integral between A and B of r squared dr. And that's just because when we're doing spherical harmonic integrals, we had to add this r squared sine theta dr, d theta, d phi, which is equivalent to the just dx, dy, dz in Cartesian coordinates. So that's where that r squared comes from. So we need that r squared there if we want to really find a probability integrating over r. We did a practice problem, but we saw how quickly this kind of problem can become complicated. So we'll hold off on that for now. So if we want to figure out the probability, then we just plot this function, right? Some people call this the radial distribution function, but let me just make sure that that is in fact what they call it. Yeah, so we call this r squared times the radial part squared. That's the radial distribution function. So if you really want to know, get a sense of what the electron's doing, you just plot that. And so if we look at that radial distribution function, r squared times r squared as a function of r, right? We said that it starts at 0 because there's no real probability of electron being at the nucleus because 0 here is at the nucleus. And it'll go out something like this. And this is for the 1s orbital. It looks something like this. And here we said that the most probable location for a 1s electron for a hydrogen, that's called the Bohr radius. It's the most probable location for an electron. But like we said, the electron still has a probability of being almost anywhere else. It goes all the way out to infinity, kind of like that. If we do the same thing for a 2s electron, so again, this is going to be r squared, this is r. Let me use a different color. It looks something like this, right? This is 2s. We said that there is a node right here. So if we were to plot this, it might just look like, in 3 dimensions, it might just look like a sphere, right? Here, if you cut through that sphere, you'll see there's a part that has one sign. There's a node in between, and then there's a part with a different sign for the 2s electron. The 2p electron doesn't have that node, right? So this is r squared, r squared. The 2p electron kind of looks like the 1s electron, like that. The probability has some maximum value somewhere. So if we draw that, so this is 2p, if you draw it, this is the nucleus and we're going out for the radius. It gets larger at some distance and then gets smaller again, kind of like that. But we know this doesn't take into consideration the angular part. And so we know for 2p, there's going to be some angular parts. And so for one situation where those that would give us 2 little lobes like this with 2 different signs along one axis. But this again, this here ignores all the angular parts. We're only looking at the radial part. So you can think of it as just looking at this half of it. If we go up to a 3s electron, there's a pattern here, right? The 3s electron will have, let me see if I can draw that nicer, 2 nodes. So a little bump, bump, even bigger bump. Node here, node here. This is the 3s electron. So if you were to slice an orbital diagram of a 3s electron, right, you'll have a probability here, a node. You'll see a different color usually around that to represent the wave function change signs, and then another node, and then this original color again to show that the wave function change sign again. Of course, I'm not drawing this to scale. Those are 3s orbitals. The 3p orbitals, similar idea. If this is the radial distribution function, this is r. It's kind of like the 2p orbital, except you add a node. Every time you go up, you add one more node. So it'll look kind of like this, kind of like the 2s orbital, in fact. There's a node right there. This is the 3p orbital. What does this look like? Well, it means that if this is the nucleus and we go out this way, the wave function will have one sign here, and then a different sign, let's use blue, out here. But these are p orbitals, right? So on this side, it'll be a little wave function there, and then the other wave function. So this is what a 3p orbital looks like. So we kind of lied to you when we said that all p orbitals look like this. More or less they do, but 3p orbital also has a node sort of right there and right there, in addition to the node along the center where the nucleus is. And 4p, you'll have more nodes, and 5p, you'll have more nodes, and so on. And then 3D, 3D radial distribution function kind of looks like the 1s radial distribution function, where it's just one single bump. And so you can see the pattern that starts to build out with these, and you can keep drawing those diagrams. But what I wanted to point out to you was just how we can understand these various orbital pictures, right? By just looking at the radial distribution functions. Any questions on these so far?
2 quick questions. So first question, is this like the case with the particle in the box where the average position is actually at the node, or not, because the probabilities are different sizes?
I mean, it might end up being the case for one of them that the average position is right at the node, but not Not that I know of. I haven't done these calculations myself. For example, in this one here, this is the most probable location, but it's not necessarily the average location, right?
Okay.
The average location might be somewhere here. Again, I don't remember what the exact number comes out to be. Does that make sense?
Yep. And then second question, do these orbital shapes only apply when they're only really apply when there's one electron? Because do like would the electron, because like if you have two negative charges in close proximity, they repel. So would that change the orbital shape, I guess?
Yes. These only apply for one electron systems. In the next chapter, what we're going to start in just a little bit, we're going to talk about more when we have more than one electron, what happens. But these only work for one electron. So a hydrogen atom or a helium atom and +1 charge and so on. But they don't change that much that we can't use them to understand what's happening. For if you're dealing with single atoms, you can keep going with this sort of picture and it gives you a good idea of what's happening. But yes, it don't the exact
For anyone
shape.
else in here, I wouldn't have done that, but I had to.
Can you pause?
It was a barking spider.
Crystal, you're unmuted.
Okay, I muted her. It's fine. So what I was saying was, if you have atoms, yeah, you can use the same orbitals. But yeah, these only work. These are only exact. These functions and these quantum numbers and these orbitals, exactly as we draw them, are only exact for one electron systems.
Okay, thank you.
Welcome. So yeah, all of these gives us an idea of what the electron could be doing in a hydrogen atom. And then finally, the last thing that I want to mention was the wave function, the hydrogen-like wave function is orthonormal. I mean, they should all be orthonormal, but if you remember what that means is if we integrate, I mean, using this Dirac symbol that we talked about earlier, a wave function with some value of n, l, and ml, let's put a little 1. I'm going to erase that and put a little 1 next to them. So some for value of n, some value of l, and some value of ml with a wave function with maybe some other value of n, some other value of l, and some other value of ml. This will be 0 if n1 is not equal to n2, or L1 is not equal to L2, or ML1 is not equal to ML2. So if any of those two numbers are different, this whole thing integrates to 0. And that's just the fact that wave functions, when we solve for them, are orthonormal, right? Or should be orthonormal. All right, so that's the hydrogen atom or hydrogen-like atom. Anything with one electron, we can solve it. We can solve for it. So we've solved particle in a box, we've solved a harmonic oscillator, we solved the rigid rotor. We've now solved the hydrogen atom or hydrogen-like atom. But things in the real world, while the hydrogen atom is a real world situation, things in the real world can get much, much more complex than that. So that's exactly what we're going to start looking at right now. So we're going to look at the multi-electron system. And by multi-electron system, I just mean any atom with more than one electron, or any molecule, all of those have more than one electron, hence we call them multi-electron. So the multi-electron system, and we're also going to look at the electron spin. And so our objectives for this, this section, which really covers all of chapter 12. Again, I'm going to pick and choose stuff from the chapter, but I'm going to just summarize the whole of chapter 12 as the multi-electron system and electron spin. So what are we going to learn about? We're going to learn about, let's use a different color. How to include electron spin in the wave function. We're going to learn how to write the Hamiltonian for systems with more than one electron, like the helium atom. That's the simplest system with more than one electron. We're going to learn to about the quantum mechanical origins of the Pauli exclusion principle, which I'm sure you've all heard of. We're going to learn about Slater determinants. That might sound strange to you, but you'll understand maybe when we get there, hopefully. We're going to learn about variation theory and something we're going to call electron correlation in multi-electron systems. And finally, we're going to be able to identify representations of molecular orbitals. Using a method we're going to call linear combination of atomic orbitals, for now just LCAOS. So that's what we're going to try to do this chapter. Anything else beyond that? Probably not going to focus on for right now. So this is going to be the last sort of cherry on top to like wrap up this whole idea of quantum mechanics and how it works for atoms and molecules. So far, we're basically just using it for small model systems. But with this, hopefully we'll be able to get an idea of how do we use this for a real molecule that you might be interested in. Is everybody good with this? Okay, looks like it. All right, so we're going to start with the electron spin. Right. So far, we haven't talked about the electron spin. So we're going to introduce the idea, because once you start dealing with more than one electron, the spin becomes important. And back in 1922, two scientists, what are their names? Stern and Gerlach. Yeah. What they did was they shot some silver atoms, vaporized, of course, into the gas phase between a piece of magnet, right? So let's say this is the north end of the magnet. This is the south end of the magnet. They shot the atoms through there onto a plate, to detect it in somewhere. Now, you would think, all right, maybe the atoms aren't affected by the magnetic field, and this should go straight through and hit this little plate, right? But that's not what they observed. What they observed was that some of these atoms bended upwards and hit a spot somewhere there. Some of them bended downwards, hit a spot over there. Again, close to a single spot, but there's some uncertainty in their position and momentum, so they kind of hit some spot. And so you could do this with silver atoms, but in fact, if you do this experiment with any atom where there's an unpaired or where there's an odd number of electrons, for example, you'll observe something similar. In fact, if you shoot just electrons through there, nothing else, just electrons, a beam of electrons, you'll also see the same thing. So why is this? So you're shooting electrons, and some of them are attracted to the north end of the magnet, some of them are attracted to the south end of the magnet. And so the conclusion here, and let me just, this is 1922, the Stern-Gerlach experiment. So what the assumption here is, so these results suggested that the electron has an intrinsic angular momentum, right? Something that interacts with this magnetic field that, and we'll call this intrinsic angular momentum, we'll call it spin. Why are we calling it spin? Is the electron spinning like a top? Well, is the electron kind of like, this is a ball, right? A three-dimensional ball. Is that the electron, and is it spinning around like this? Well, here's the thing, we don't know, right? Is the electron a ball? How big it is? What is the radius of this electron, or how tiny it is? We don't know. As far as we know, electrons behave as waves, probability waves, right? And if you try to find a specific location or the size of an electron, there's always going to be uncertainty. So we don't know whether the electron is a ball spinning or not. So the answer is we can't know for sure. If anybody tells you that's what it is, I would be skeptical. If somebody tells you that's not what it is, I would also be skeptical, because like we can't know, because we can't measure things that small. Because just not because we don't have the instruments, but because of the uncertainty principle, we can't get down to that level. The electrons won't appear as a solid particle, but it would appear as some probability wave. So we can't measure the position or shape of the particle and see how it's spinning, but we can measure the total angular momentum, the total, let's call it the total spin angular momentum. We're going to use this operator, right? Capital S squared, which is similar to L squared for orbital angular momentum that we talked about earlier. So the L squared measure the angular momentum, the electron going around the nucleus. This spin or total angular momentum will be measuring the angular momentum of the electron spinning. If it is spinning, we don't know, spinning around itself like a top. So we can measure total spin angular momentum, and the z component of the spin angular momentum, and that will be sz, which is similar to lz for orbital angular momentum. In fact, let me just highlight a couple of things. So the first one is called total spin angular momentum, or SC. The second one is z component of the spin angular momentum, or SC. Sorry, this top one is S squared. That's essentially what Stern and Gerlach were measuring. They were measuring the z component of the orbital angular momentum, right? So you can imagine that's usually how they set this up. This is the z-axis, right? Some electrons go up, some go down. So some would have a positive z component, and some would have a negative z component, right? Now, when we wrote LZ or L squared, we had like a form for them, right? We had an operator for them. We can apply them to the wave function and those kind of stuff. But honestly, I won't be able to tell you what these operators look like. I honestly don't know. I don't know if anybody knows, but maybe somebody does. But when we apply them to the wave function, when we try to measure the spin angular momentum, right, we get back something like that has a similar form to when we use L squared, except instead of L, we're going to use lowercase s. And we found that in this case, s is just equal to a half only, nothing else, right? When we use the sz, so the z component of the spin, and we apply it to our wave function, we get back ms times h bar times the wave function. And this ms would only be plus or negative a half and nothing else. Because this is only ever a half and nothing else, we can usually ignore that quantum number s, because it's always going to be a half, so we don't need to write it. But ms can be two different values, plus a half or minus a half. So in the experiment like this, you can say, well, maybe this is ms equals plus a half, maybe this is ms equals negative a half. So there's only ever going to be two values there for an electron, right? Everybody still with me here? So we can measure the spin, we can measure the total spin, we can measure the z component of the spin. But like I was saying earlier, we don't know what this operator is, we don't know what this operator is, so we don't even know what they should look like when we plug them into our equation. So how do we add spin and this ms value to the wave function, right? We know we can add how the other quantum numbers are included in the wave function, right? They make up the radial part or the angular parts of the wave function. But how do we add this idea of spin or z component of the spin to the wave function? And more particularly, we're interested in this, not so much this, because this is always going to be a half. It doesn't change from electron to electron. So how are we going to add the ms value to the wave function? Well, the easiest way to do it is to just add some symbol for it, because we don't know what it looks like. So we're just going to add a symbol for it. So what we're going to do is we're going to say the total wave function, which depends on the x coordinate, the y coordinate, and z coordinate of the electron, also depends on the spin of the electron, right? And we're going to say that that depends on a wave function that only depends on the x, y, and z coordinates times the spin function. So this is a spin function. And again, it's just a symbol. We don't actually have a function to represent the spin. It's just a symbol for a function. Your textbook has it slightly differently, but I'm going to use this. This is sigma, right? Greek letter for S for spin. That's why I'm using it, right? Now the sigma is going to be alpha if ms is equal to positive a half. This is my convention. And sigma is going to be beta if ms is equal to negative a half. So those are the two options. Remember, ms can only be positive or negative a half. So this sigma could only be alpha or beta. So sometimes you hear people talk about alpha spin and beta spin for electrons, maybe. This is sort of what they mean. So all we're doing is multiplying the wave function by some symbol to represent the ms value, because we actually don't know what the spin is, what it's doing, and how it fits together with the rest of the stuff. Is this a hack? Yes, maybe. Does it work? Also, yes. So why not use it, right? So here's the thing. When we do this, we're going to say that if you measure the z component of this alpha function, you're going to get back plus a half times h bar times the same alpha component, right? This is why we say ms is positive a half. And the z component times the beta function will get negative a half times h bar times the beta function, right? These set up eigenvalues equation. So if you take the z component, multiply it by the wave function, right? That's the same as saying you're taking the z component of the spin operator times the part that doesn't depend on spin times the part that, let's say, does depend on spin. This whole thing would come out to be plus a half h bar times that, which is basically saying plus a half h bar times the wave function. That's how we include spin in our wave function. We just say that the wave function has this spin part, and when you apply this operator on this spin part, it gives you the z component of the spin. We're just making things up now. They're just symbols because we don't know what alpha and beta actually looks like. Like I can't plot it on the graph for you, kind of thing. If you do this with the beta spin, it'll just give you minus a half for the ms value. And in case you're wondering how this all comes together for a hydrogen atom, right? So now a hydrogen atom will have 4 quantum numbers. It'll have N, L, ML, and MS, right? And if this MS is plus a half, then this wave function will be the R part, the theta part, the phi part. And since it's plus a half, we'll multiply all of that by alpha. And if it's N, L, ML, and MS, but MS is negative a half, then it'll be, the R part, the theta part, the phi part, times some symbolized function beta to represent MS equals negative half.
Question.
Yes.
Is the spin function something we don't know yet, or is it something that just by its nature we can't know?
That's a very hard question. I hesitate to say things we can't know. Like we can't ever know X or we can't ever know Y. Those are very strong words, and who knows, 5 years, 10 years, 500 years from now, somebody might be like, no, we can know this. Like, what are you? You guys are stupid. We don't know. Or I should say, I don't know, right? Who knows what those theoretical physicists come up with? I'm just a humble chemist, man. I don't know. This is how we treat it in chemistry. Who knows what those guys that deal with like particle physics and Higgs boson and all that kind of crazy stuff. Who knows what they know? So
Right.
here, sorry, you're welcome. So here's a complete description of an electron. We just needed to multiply the spin part. So before, when we just had this part here, we called it an orbital, right? We call it an electron orbital, and we said we can fit 2 electrons in an orbital. Well, this is how we can fit 2 electrons in an orbital. The combination of the orbital plus the spin part, right? That you can call out a spin orbital. So that's just the language. If you hear somebody talk about an orbital, it just means the part that don't depend on spin, and in which case you can fit 2 electrons in there. If they include the spin, it becomes a spin orbital, and there's only really 1 electron it can fit in there. But again, I'm getting ahead of myself. We're going to talk about why we can only fit 1 electron in there in a bit. Like I said, alpha and beta are just symbols for functions. We don't know what they look like, or I don't know what they look like. But what they do tell us, those alpha and beta, they tell us how they react to magnetic fields, right? Doesn't matter which direction you point the magnetic field. If there's a north end here and a south end here, one MS value will go one direction and the other will go the other direction. Or the north magnet could point in up and down, and it'll be the same idea, right? One spin will go in one direction, one spin will go in the other direction. All they tell us is how those electrons would react to that magnetic field. By definition, we say it's the Z component, right? That's just by convention, but it could mean any component, the X or the Y or the Z. But just like the angular momentum, you can't know the X component of the spin and the Y component of the spin at the same time. For example, this commuting with the X component will not be zero, or and so on and so forth. So you can know one of the components, one of the directions of the spin, not more than one. So basically, if you had a 4-magnet setup, north, south, north, south, like we don't know the path the electron is going to take through here, right? If that makes sense. So that's spin. Some weird intrinsic, we say it's intrinsic because the electron has a spin. Where does the spin come from? We don't know. It's just kind of like how, well, I don't have a good example, but my name is Abe, right? That's just an intrinsic value for me. Where does it come from? Well, I know where it came from. My parents named me, but it's just a property of the electron. What it's doing and how it has it, nobody knows, or I don't know. So now that we have the electron spin, we actually have all the pieces to put together a wave function for any electron anywhere. Doesn't have to be one electron, could be 2 electrons and more, or more than 2 electrons, right? So we're going to do exactly that. We're going to put together a system with more than 1 electron for the second simplest atom in existence. And that will be the helium atom. So let's see what the helium atom might look like. So here's the nucleus. I'm not going to separate out the nucleus into protons and neutrons and all of that because the nucleus is so tiny compared to electron that we're not going to bother with that part. And it has 2 electrons, right? So the helium atom has a nucleus and 2 electrons. I'm just going to say there's 1 electron over here. We call it electron 1. And it doesn't matter where I put them, right? Because we're just trying to develop a model here. But there's my second electron somewhere else. So the nucleus here, right, this is the nucleus. We're going to say that the mass of the nucleus is going to be m subscript n, just to keep it simple, right? The mass of the nucleus. The charge on the nucleus, what's the charge on a helium nucleus? I know you know, I'm just pausing. Yep. So it's +2 E, right? E is the elementary charge, right? So it's +2E. This electron has mass of the electron, and the charge is -E. And here, same thing. The mass is the mass of the electron, and the charge is -E. Can you guys still hear me?
Yes.
Yes.
Okay, my computer's frozen. So let's take a 2-minute break or 3-minute break while I restart my computer. This tends to happen sometimes. So I'll see you in about 2 or 3 minutes because my computer's frozen. Sorry about that. All right, I am back. Thanks for your patience. I think every time I'm on Zoom, this tends to happen. Don't know why, but this is the first time it actually happened in our class, I think. All right, so we're talking about a helium atom has a nucleus, has 2 electrons. Nucleus has a mass and a charge. Electrons have a mass and a charge. And just to sort of complete this pictures, we also need, let's just specify some distances between each of these little things, like that, right? So the distance between the nucleus and electron 1, we'll say is R1. Distance between the nucleus and electron 2, we'll say is R2. And the distance between the 2 electrons, we'll say is R12. And that's important because if you recall, the potential between two things with 2 charges, right? Coulomb potential is the charge of one times the charge of the other. Let's use A and B, divided by 4 pi epsilon naught times RAB, right? Where that's a distance between them. So that's why we needed to know the distance between them. So this is a very classical picture of what a helium atom is, but it's going to be very useful for us to set up the quantum mechanical model for the helium atom, which is what we're going to do now. So remember, whenever we're solving any of these quantum mechanical systems, the very first step is always to write the Hamiltonian. So what is the Hamiltonian? Well, the Hamiltonian we know is the kinetic energy plus the potential energy, right? There are 3 different parts to the system. Again, we're keeping the nucleus together. We're not separating it out into protons and neutrons. So the kinetic energy will be the kinetic energy of the nucleus plus the kinetic energy of electron 1 plus the kinetic energy of electron 2, right? 3 pieces, 3 particles, 3 different kinetic energy. What about the potential energy? Well, we have the potential energy between electron 1 and the nucleus, right? That's basically, we'll have a potential energy between any 2 pair of things. So we'll call the potential between the electron 1 and nucleus just the potential 1. The same for potential 2 and the electron 2 and the nucleus, we'll call it potential 2. And the potential between the 2 electrons, we'll call it potential 1, 2, kind of like that, just to give it symbols. All right, so the kinetic energy of the nucleus, that's negative h bar squared over 2 times the mass of the nucleus times the second derivative of the coordinates for the nucleus. We're going to symbolize it all as this nabla squared with the subscript n, right? So that's the kinetic energy of the nucleus right there. We're going to add the kinetic energy of the first electron, so it's negative h bar squared over 2 mass of electron times the second derivative of the coordinates for that electron, right? Plus the kinetic energy of the second electron, right? 2me nabla squared for the coordinates of the second electron, so subscript n. V1 here, that's a potential for the first electron on the nucleus. Plus the formula is here, Coulomb potential. So the charge on the electron times the charge on the nucleus, that's what QA times QB would be. So it's negative E times positive 2E, right? That all comes out to be negative 2E squared, right? Divided by 4 pi epsilon naught R1, because that's the distance between them, R1, we said. So that's the potential for the first electron and the nucleus. We have a potential for the second electron and the nucleus that looks pretty much identical, except it's now radius R2. So that's V2. And now we need a potential between the 2 electrons. So electron 1 has a charge negative E, electron 2 has a charge negative E. So you multiply those 2 together and you just get E squared. So it's E squared 4 pi E naught, and the distance between the 2 of them we say is R12. So I'm going to use this, I'm going to group some similar terms together, right? So this is our Hamiltonian. This term depends on the coordinates of the nucleus. this term depends only on electron 1, and this term really only depends on electron 1, right? And then we have, let's see, this term here, and this term here only depends on electron 2. And there's this term here that depends on both of them. So I don't know, we need to give that one its own thing. So that's the third part. So those are the different sort of parts to this Hamiltonian, right? So this green part, we'll call that the nuclear Hamiltonian. So the Hamiltonian is broken down to a Hamiltonian for the nucleus, right? That's the green part. It's just the kinetic energy of the nucleus. Plus, this is the kinetic energy of the first electron. This is the potential energy of the first electron in the nucleus. So I'm going to call that electron 1 Hamiltonian. This part here has a kinetic energy of electron 2 and a potential energy of the electron 2. So I'm going to call it the Hamiltonian for electron 2. And you know, to make this easy, I'll just put 2 instead of all that. So it's easier to write. We'll put 1 there. And then finally, this last part here is the repulsion between electron 1 or 2. I'll call that the Hamiltonian between electrons 1 and 2, kind of like that. So when you can write stuff as different sums here, we need to solve, remember, the Schrodinger equation, right? That equation. This is what we need to solve. This is the Hamiltonian that we just wrote here. We talked about how for the wave function, once you could separate it out into a nuclear part and everything else that's not a nuclear part, you'll have a nuclear wave function and an electronic wave function. Remember that? We call this the Born-Oppenheimer approximation. And we say that the nuclear motion is so slow compared to the electrons that we can ignore it. So we separate it out into 2 parts and we're going to ignore the nuclear motion. So all we're going to be interested in is the electronic parts. So the only thing that we're going to be interested in here is the electronic Hamiltonian, right? Kind of like that, which basically only has a Hamiltonian for electron 1, a Hamiltonian for electron 2, and then the interactions between electrons 1 and 2. That's the Born-Oppenheimer approximation, and it will just make our life simpler because it got rid of the entire nuclear part. So this is electron 1 only. This here was electron 2 only. And this here was electron 1 with electron 2 interacting. All right, so we have our Hamiltonian. We simplified it using the Born-Oppenheimer approximation. All that did was take out the nuclear kinetic energy. That's all it did, because the kinetic energy of the nucleus would be so small that we don't need to worry about it. How do we find a wave function? How do we find this wave function? Well, before we even find it, let's see if we can figure out what it might depend on, right? So the wave function should depend on the x-coordinate of electron 1, the y-coordinate of electron 1, the z-coordinate of electron 1, the spin, remember as sigma is representing the spin of electron 1, the x-coordinate of electron 2, y-coordinate of electron 2, z-coordinate of electron 2, and the spin of electron 2. So those are all the various different things we have to worry about in this wave function. And this is only for 2 electrons. You can imagine what this looks like when we go to 3 electrons or 4 electrons or any reasonably sized molecule. Remember when we were solving things like particle in a box and stuff like that, we said if it has more than 1 variable, it was too complex and we tried to simplify it, right? This has 8 variables that we need to worry about. How do we even begin to simplify this matter? Short answer is we can't. This problem falls under a class of problems in mathematics called a three-body, or sometimes you just hear the word many-body because it works for three-body or four-body. Many-body problem that is impossible to solve analytically. What does that mean? Well, there's at least 3 bodies in this problem, the nucleus and the 2 electrons. And so no matter what you do, there is no good function for this wave function. Basically, in all of mathematics, we don't have a function for that. Like, e to the x, that's a function, or sine of x, that's a function. Nobody in maths has come up with a function to describe 3-body motion. I blame mathematicians. I feel like we'd get much farther in life if they had come up with a solution. But no, we don't have the mathematics to describe this. That doesn't mean that we can't try to solve it, right? But we're gonna have to here's where we're gonna have to make some assumptions and some approximations. So far, everything else that we've been doing this semester, I mean, we've made the Born-Oppenheimer approximation, that's one, sure. But here's where we're gonna have to like really simplify things.
What is the DVX? What is the what is just ahead of the red arrow that points to the purple?
I just said that there were there. We have functions like e to the x and sine x and all those kinds of stuff that we were able to use to describe the wave functions for earlier systems, like particle in a box. We use sine x. For the for the hydrogen wave function, there's like e to the x in there, and there's some x to the some power. Basically, we have different types of functions to describe those. But when we come to this 3-body problem or this many-body problem, we don't have any function in existence, as far as I know, that could describe them.
Okay.
We haven't nobody has come up with a function to describe them yet. So there's not solvable analytically, which means that we can't write this as exactly as some function of all those different combination of things. It's not possible.
Okay.
So how do we move forward here then? Because are we stuck then? Is quantum mechanics useless because we can't solve anything for more than 1 electron? Well, yes and no. There are ways, like I said, that we can go around doing this. But before I jump into all of that, how we can actually try to solve this, let's take a quick break here and give you a small exercise to do based off of something that we just did, which is I want you to write the full Hamiltonian and the electron Hamiltonian. So that's the Hamiltonian with the Born-Oppenheimer approximation, for the lithium atom. So I'm going to just draw what that looks like. If this is the nucleus, right? Let's say this is electron 1, this is electron 2. I'm just going to put them randomly. Electron 3. The distance here we're going to call R1. This is R2, R3. Distance between electron 1 and 3 is R13. This is R12. And that distance there is R23. So I want you to write the full Hamiltonian and the electron Hamiltonian for that lithium atom. So take some time and try to write it all out. the mass of the nucleus here will be Mn. The charge on the nucleus is positive 3e, as you probably figured out. So an exercise like this is just really what we call bookkeeping, in that I'm sure you know how to do it. It's just, are you accounting for all the parts? When and if you're done, give me some indication that you are. So this is all for lithium atom, right? Imagine how quickly the complexity of this increases with number of electrons and number of nucleus in your system. If you were to write this for a water molecule, pretty small molecule, H2O, you'd have 3 nuclei, right? For each of the hydrogen and the oxygen, and you have 10 electrons, right? So for a simple water molecule, the amount of terms you have to keep track of just becomes crazy. So yeah, if with computational tools, you can automate all of that and make it simple. But this can become quite complex quite quickly.
When you have electrons hybridized in orbitals, do you treat those terms still the same?
Electrons
like the bonding electrons?
Yeah.
Like for a water molecule.
So here's the thing with quantum mechanics. We don't make any assumptions about anything about where those electrons are. I just drew them somewhere because I have to draw them on a page. but those electrons could be anywhere. We don't make any assumptions about them, what they're doing, where they are, who they're friends with. No assumptions. We just put them down on the page, write them, and solve them. And one of the things that these ideas of bonds that we learn about in chemistry are correct in a sense, but from a quantum mechanical point of view, I don't even think about bonds in that sense. You can think of, and we'll talk a little bit about what makes up bonds, but bonds are really just when the electron spends a lot of its time between two atoms rather than on one atom itself. But you find that by solving the equation and then trying to find the probability of where that electron is. And if there's a high probability that it's between two atoms, then okay, we call it a bonding electron. But yeah, when you're solving quantum mechanical equations, we make no assumptions about how atoms are put together or any of that. We don't even make assumptions about where the nuclei are, right? So in the case of a water molecule, you know, it could be something like that, which we know what a water molecule is, but we could set it up like that and try to see what happens. And if you set it up like this and you let the nucleus move, eventually it will what we call converge to something like that. Like, we don't make any assumptions. We let the electrons and nucleus go where they want. All right, so let's write this Hamiltonian down. Right, this is a 4-body system, 1 nucleus, 3 electrons. So the Hamiltonian will be, as we know, the kinetic and potential parts. So it will be the kinetic energy of the nucleus, kinetic energy of electron 1, kinetic energy of electron 2, and kinetic energy of electron 3. The potential of electron 1 in the nucleus, the potential of electron 2 in the nucleus, the potential of electron 3 in the nucleus, then the potential between electrons 1 and 2, the potential between electrons 2 and 3, and potential between electrons 1 and 3. Lots of terms, but those should be all of them. Kinetic energy of the nucleus, negative h bar squared over 2 times the mass of nucleus times the second derivative of the nuclear coordinates. Kinetic energy of electron 1, like this. Kinetic energy of electron 2. Kinetic energy of electron 3. Potential of electron 1. Electron charge is negative E. Nuclear charge is positive 3E. So negative E, positive 3E comes out to be negative 3E squared. 4 pi epsilon naught R1. And there's another term, 4 pi epsilon naught R2. And another term for the third electron, 4 pi epsilon naught R3. Now we need the potentials between each of the nucleus. Sorry, between each of the electrons. So it'll be E squared over 4 pi epsilon naught R12, 4 pi epsilon naught R13, and then E squared 4 pi epsilon naught R23. So those are all the terms in the Hamiltonian.
All right, where did you get the 3?
The 3, which 3?
The 3 for the
Here?
Yeah.
So the Coulombic potential is charge on one times the charge on the other. And so the charge on the nucleus is positive
3, 2.
And then it's negative E, so it's negative 3E squared.
Okay. Okay.
So that's it. That's the total Hamiltonian, or the full Hamiltonian. And if we want to do the Born-Oppenheimer approximation, the Born-Oppenheimer Hamiltonian, we ignore that part. The part that depends on the nuclear kinetic energy. Everybody with me? All looks good? All right. So that's how you write the Hamiltonian for a multi-electron systems. This gets more and more complicated the more terms you add, but it's bookkeeping, like I said. You just keep track of all the terms and you can figure it out. How do we solve this wave function? I don't know, man. This is, if we knew how to solve this wave function for systems with more than one electron, and there was a paper recently that somebody solved it for helium doing some magical trick. I haven't read that paper yet. I should. But if we know how to do this, I would be out of a job as a theoretical chemist, because this is what I do. I try to figure out how to solve these problems for more than one electron. But we're gonna do some assumptions, and this is gonna lead us to something we're gonna call the Slater determinant. So determinants and the Pauli principle. All right, so for the helium atom, we said the electron Hamiltonian has a term for electron 1, a term for electron 2, and a term for sort of the interactions between electron 1 and 2. Let's ignore this part. I know, it's wrong, probably, very wrong. But let's ignore it for now, because this is easy. There's a part for one electron and a part for another electron. We can separate them out. Here, we can't separate them, they're together. So we're gonna ignore that part for now. So when you do something like this, you can say that the wave function has two parts. A part for electron 1 and multiplied by a part for electron 2. Right? In fact, instead of using this capital psi, I'm going to use lowercase psi like that. Like that. So there's going to be a wave function for electron 1, a wave function for electron 2. I'm using lowercase psi just because they're not real. They're just an approximation. I mean, a lot of it is going to be approximation from here on out. But if you look at this Hamiltonian, this electron 1, if you remember, the Hamiltonian there is just the kinetic energy for that electron plus the potential energy for that electron. Nothing in here has anything to do with the second electron. In fact, it just looks exactly like if you just have one electron there, right? Kind of like what we did for the hydrogen atom. So we can use a hydrogen atom or hydrogen-like wave function for that one. And then we could also use a hydrogen-like wave function for that one, just as an approximation, right? Because that's what they are. They're like one electron alone interacting with a nucleus. So we're going to make this approximation. And so the wave function then for either electron 1 or electron 2, we're going to say is a hydrogen-like wave function with quantum numbers NL and ML. And then we're going to add in some spin in there as well. So it's going to be like one hydrogen atom wave function multiplied by another hydrogen atom wave function, because we're ignoring how the electrons interact with each other. We call this model a product wave function. Product wave function. You know, it doesn't even matter what we call it because it's never going to come up in a test. Okay. So this is an approximation. We ignore the electrons interacting with each other. Next, we're going to assume we're working in the ground state only. So let's only work with the ground state. And for those of you wondering, I think we talked about this, but the ground state is the state or function with the lowest energy. And we're going to work with the ground state only because it's going to simplify some things, and we know what the helium atom should be doing in the ground state. We can measure that. So in the ground state, if you recall, N will be 0, L will be 0, no, N will be 1. L will be 0, ML will be 0, and MS could be positive or negative a half. That's our ground state. All of this that makes up the orbital, N equals 1, L equals 0, ML equals 0, that's the 1s orbital. So I'm just going to use 1s to represent all of this. So this wave function for electron 1 will basically be a 1s orbital multiplied by the spin part, right? And that spin part could be positive a half or negative a half. So I'm just using the general symbol sigma. So the total wave function will be an electron wave function for the first electron, which we said would be a 1s times the spin. And the second one will be the same thing, a 1s orbital times the spin. To separate these two, I'll put a little subscript 1, 1 to specify that's for electron 1, and then 2, 2 to specify that's for electron 2. I'm going to go up all the way here, and I'm going to change this equal sign to an approximate equal sign. Because the wave function is not exactly this, it's that because we ignore this part here. So I'm going to use approximates just so that we understand that this is not real. But it'll give us some insight into what's happening. So there we have it. The wave function for helium atom will be a 1s wave function for an electron times the spin part, multiplied by the 1s wave function for the second electron times the spin part. And we can stop there, right? We will be like, oh, yeah, in a helium atom, there's the electrons are in the 1s orbital. We kind of learned that in high school, maybe. For helium atom, electrons are in 1s orbital. And then there's the spin part. But my question to you is, what's the spin part? And is this 1s orbital stuff even, like, what does it mean to be in 1s orbital? We'll stop there though, because the next part, I don't want to start it and then not be able to finish it. But the next part, we're going to talk about what the spin part looks like and why that ties into the Pauli exclusion principle, which is something that we've heard of probably since high school, but like, where does it come from? Yeah, so we'll stop there. We'll pick up from this point. And yeah, any questions so far? No? So when we start talking about spin, things get hairy because spin is not something we can imagine. It's not a function we can draw. For me, it's like, what is this thing? Like, why can't we figure it out? So if you're confused about spin, that's okay. I don't even know what it is. So please ask your questions. And just as a reminder, Thursday, if you want bonus points on your second exam, you need to submit your work, including a short paragraph about where you went wrong and your exam so that I can compare the two on Thursday during class. Sounds good? Any other questions? All right, so let's stop there. My aim next Thursday is our third exam. My aim is to finish up the notes that I have on this chapter. And so the exam will be primarily through the end of chapter 12. But again, it'll depend on how far we get through next Tuesday. All right, just a reminder, the 5th Jupyter notebook was due last Sunday and the 6th one is due basically the Sunday before finals. But it's super quick and it's exactly on multi-electron systems and how to solve them. Very short. All right, I'll see you guys on Thursday. Have fun.
I have a quick question.
Yep, go ahead.
You said the test corrections were due this Thursday, right?
Yes.